We did a part 1 and part 2 on phasors and phasor forms for vector. So a lot of the details are explained in that part. But basically what we have is a real vector, vectors that we normally use, which is a function of position and time. And we can write that as a phasor form of the vector, a complex vector, which is only a function of position times e to the I omega t. And this works for sinusoidal conditions of some parameter. And usually that parameter is t. It could be something else, maybe q, and you'd have a q here and a q here and then. But the real vector is equal to the real part of this complex vector. So what we want to show is how to go from one to the other by using an example. And let me just mention that the sub p that we're using here denotes the phasor form of the real vector. So let's say we start out with this vector for the phasor form, only a function of position. 6 minus 8i, complex number I, cosine x, unit vector x, and this term times the unit vector y. It's just an example. It doesn't have any real significance. So to find the real vector, we take the real part of this vector multiplied by e to the I omega t. That's what we described over here as the relationship. Before we go on, we'll just say quickly with complex numbers. Let's say we have the complex number u plus iv. We're doing this because we have this complex number here. And that's equal to r cosine theta plus I sine theta, r e to the I theta. And theta, the arctan of theta, is equal to v over u. So for our case here, we have 6 minus 8i. That's equal to the square root of the sum of these two numbers. 36 plus 64 gives me 100. Square root of 100 will give me 10. And e to the I theta, where theta is the arctan of minus 8 over 6. Again, uv, the u is 6, the v is minus 8. The arctan is v over u, so that's a minus 8 over 6. It's good often to keep track of which quadrant you're in by showing the negative sign on the correct quantity, in this case, the v. So what we have in the square brackets here now, we can write as this quantity here, 10e to the I theta, cosine x, unit vector x, plus the quantity times y, e to the I omega t. So we can take the e to the I omega t through, and we'll have 10 e to the I omega t plus theta. E to the omega t times I to the theta is going to give us omega t plus theta, I, e to the I. That's the x component plus the y component. Here we have I pi over 2, I omega t. When we multiply through, we can combine it as a sum, I omega t plus pi over 20 over x plus y times the unit vector y. So that's what's in this square brackets. We're going to take the real part of that. And if we apply Euler's formula, you can see that we would get 10 times the cosine of x. Let's see, I missed a cosine of x in here. 10 times that cosine of x, cosine from the Euler's formula of omega t plus theta, and then we'll have the I term, but we're taking the real part of it, so that goes away, and that's for the unit vector x, the x component. And then for the y component, we're going to have the cosine of omega t plus pi over 20, and we're taking the real part again, so the sine part from the Euler's expansion will go away, so we're just left with the cosine, y component. And so we found what the real vector is in terms of these quantities, and the theta in this expression here is given by the arctan of minus 8 over 6, which is approximately this many radians, or approximately that many degrees. And what we'll do in part 4, we'll start with this, and we'll try to get back to the phasor form this. So we'll see how that's done in part 4.